Hello and welcome to my presentation. My name is Amena Saiyed. I'm excited to share with you my research on using a heuristic technique known as particle swarm optimization to help predict diabetes. We will explore how this technique can help us choose the best important factors from a dataset, making our predictions more accurate and effective. Let me start by explaining what is a heuristic technique. Heuristic techniques have revolutionized problem solving in fields ranging from computer science to operations research. At their core, heuristics are strategies or methods that simplify complex problems, allowing us to find satisfactory solutions more effectively than traditional approaches. Rather than exhaustively researching every possible solution, or option, heuristics leverage rules of thumb, patterns, or intelligent guesses to navigate vast solution spaces. Imagine trying to find a way through a dense forest. Rather than mapping every single tree, you might follow trails, recognize landmarks, or even follow the sun. Similarly, heuristic techniques guide us through integrate challenges by employing smart shortcuts. These techniques are particularly valuable when dealing with optimization problems, where the goal is to find the best solution among many possibilities. For instance, in machine learning, heuristics helps us in feature selection, model training, and hyperparameter tuning as well, ultimately enhancing model performance and reducing computational time. In this context, one of the most notable heuristic techniques is particle swarm optimization, which I'm using in my research, which mimics the social behavior of birds to solve complex optimization tasks. Today, I will share how I applied PSO to predict diabetes more effectively through careful and important feature selection. Particle swarm optimization (PSO) is a nature inspired algorithm. PSO is a population based optimization technique which is inspired by the social behavior of birds flocking. Let us take an example how the mechanics of PSO works and how they are inspired by the behavior of birds. Imagine a flock of birds flying over a large field, all searching for food. None of them knows where the food is, but they can see how close they are to it and also keep an eye on where other birds are finding food. In this way, the birds communicate in the swarm and find the optimal solution, in which here this optimal solution is the food. Here, the end goal is to find the food, and each bird makes decision based on two things. The first one is its own experience, means where the bird has found food before, and the second thing is learning from others, which is where the other birds are finding food, the bird would communicate with each other and find the optimal solution, in which here it is finding the food. So taking the inspiration from flocking behavior of birds, I have chosen particle swarm optimization as a heuristic technique to solve complex optimization problem. It is really very important to understand the mathematical foundation behind a particular algorithm. Let us understand some terms to define our mathematics behind this nature-inspired algorithm, which has two main equations, velocity and position. I may sound technical, but let's understand it in the context of birds, as it is inspired by the social behavior of birds. Consider birds as solutions, the food as the goal, learning from experience as personal best, and learning from others as global best. Let us understand the two main equations of PSO, velocity and position. Velocity equations consist of several components which are really very important to make a decision for a bird. The components are inertia weight, which balances the exploration and exploitation in the algorithm, the C1 and C2, which are cognitive and social constants respectively, and they control how much the particle or the bird is influenced by its own best known position, which is we saw that is a personal best, and R1 and R2, which are the random numbers between 0 and 1, the PB, which we understood that is personal best position of the ith particle, and the global best position found by any other particle in the swarm. And Xi here is the current position of the ith particle in the solution space. The second equation here in PSO is the position update equation. Position update equation simply moves the particle or the bird in the solution space based on its current position and its updated velocity. This shift reflects the exploration of new potential solutions guided by both personal and global experiences. After applying particle swarm optimization, I tested PSO on the IEEE CEC 2017 benchmark functions. There are total 28 benchmark functions which consists of unimodal function, simple multimodal function, hybrid function and composite function. I implemented all the 28 functions, and this allowed me to test the PSO's effectiveness on challenging problems. In my research, I sought to improve the performance of particle swarm optimization (PSO) by integrating principle from GA genetic algorithm, which is an evolutionary algorithm. This hybrid approach, known as IPSO, which is improved PSO, leverages the strengths of both techniques to enhance optimization outcomes. Why did I combine PSO and GA? PSO is effective at exploring the solution spaces, but it can sometimes converge prematurely to suboptimal solutions. On the other hand, GA genetic algorithm excels in exploring diverse populations and maintaining genetic diversity through selection, crossover, and mutation parameters. By merging these two approaches, I aimed to strike a balance between exploration and exploitation. I used two parameters from the GA, which is crossover and mutation. I implemented a crossover operation where selected particles exchange information about their positions and velocities. This allows promising solutions to share attributes, creating new particles that inherit beneficial traits from their parents, thereby exploring the solution space more effectively. And to maintain diversity and prevent premature convergence, I introduced a mutation mechanism. Random changes are applied to certain particles, positions, and velocity. This stochastic element encourages exploration of new areas in the solution space, preventing the algorithm from getting stuck in the local optima. By incorporating these GA parameters into PSO, the IPSO algorithm showed significant improvements in performance when tested against benchmark functions. It not only enhanced convergence rates but also improved the quality of solutions, demonstrating the effectiveness of this hybrid approach. To sum up, integrating genetic algorithm principles into particle swarm optimization created a more robust and adaptive optimization framework. This hybrid model capitalizes on the strengths of both the methods, resulting in improved performance in complex optimization tasks, one of which I am using, which is feature selection for predicting diabetes. As a real-world example, I considered feature selection for predicting diabetes using particle swarm optimization. So let us understand what is feature selection. Feature selection is a very important process in data science that involves identifying and selecting the most relevant features from a dataset for model training. This step is particularly important when dealing with complex datasets as it directly impacts the performance and interpretability of the predictive models. There are several reasons about feature selection and its importance. Feature selections improved model accuracy, reduced complexity, faster computation, enhanced interpretability, and data collection efficiency. In summary, feature selection is vital in data science for building robust, accurate, and interpretable models. By focusing on the most relevant variables or features, we can improve predictive performance and derive actionable insights, ultimately leading to better outcomes in fields like healthcare, finance, and many more. For this project, I used the PIMA Indians Diabetes dataset, which is sourced from the UCI repository. This dataset contains of 8 features related to diabetes, such as pregnancies, glucose level, blood pressure, skin thickness, insulin, BMI, which is body mass index, diabetes pedigree function, and age. And the target variable is a binary outcome indicating whether a patient has diabetes, which is 1, or not, which is 0. The important thing about this data set that all the population, all the audience is female. Let us understand how I applied particle swarm optimization for feature selection to predict the diabetes. There are several steps which I did, starting with initialization. In PSO, each particle represents a potential solution, which in this case is a subset of features. Initially, particles are randomly generated to form a swarm, with which particles have a binary vector that indicates whether a particular feature is included, which is 1, or excluded, which is 0. The next one is fitness evaluation. The fitness evaluation of each particle is assessed using a classification model, typically random forest or XGBoost. The model's accuracy serves as the fitness function evaluating how well the selected features can predict the diabetes. Personal and global bests. The third point here are the two decisions which we studied before, that the bird makes two decisions based on two things, personal best and global best. So each particle tracks its personal best position, which is the best feature subset it has found, and the global best position, which is the best feature subset found by any particle in the swarm. This information drives the optimization process. The other important parameter is velocity and position updates. Using the PSO velocity and position update equations, each particle adjusts its position based on its own experiences and the experiences of the swarm. This allows the particles to explore new subsets to features while converging towards the optimal feature of the subset. And the fifth one is the iterative process. And this process repeats for a specified number of iterations or until convergence is achieved, meaning that the particles are no longer making significant improvements in their fitness. Using the PIMA Indians Diabetes dataset, my application of IPSO combined with the XGBoost classification model achieved an impressive accuracy of 91.01%. This process highlighted the significance of specific features such as glucose levels, which is a critical predictor of diabetes risk, blood pressure, which is strongly correlated with diabetes development, and BMI, body mass index, which is a significant risk factor. In conclusion, my exploration of particle swarm optimization for feature selection has demonstrated the power of heuristic techniques in improving predictive models. By carefully selecting relevant features, we can simplify our models and enhance their progress. For the analysis, I plotted some plots using matplotlib library in the Python. As I applied the basic PSO and the IPSO, both the algorithms with the classification models, random forest and XGBoost, I mapped their time complexity, the convergence plots, and the features distribution from the dataset. As I still have time, I am currently working on improving my results and analysis, the mapping process, like how can I show or how can I plot my algorithm is best. So I'm currently I'm trying to achieve, to implement more measures to check my algorithm. Last but not the least, I would like to extend my heartfelt thanks to my supervisor, Dr. Indubala, for her guidance and a constant support throughout this research. Thank you for your attention. I am happy to take any questions or any further discussions. You can reach me at my email I have mentioned on the screen, and I hope you find my research more effective. Thank you for your attention.